Hey there, we are in Lesson 10. Today, in Lesson 10, we are going to learn how to calculate the rate of change of a function over a specified interval. Okay, when we talk about rate of change, often we're talking about slope. And you guys know that. And we also, really important, need to understand that an exponential function, unlike a linear function, has different average rate of change values for different intervals. You think about it, if we're exponentially growing, our average rate of change between these two, that's a bad line, is going to be different than here. Okay, our slope increases as our function increases. Or if we're decaying, our slope is steep here and less steep here. All right? So that's what that means, and that's what we're going to learn today. So let's dive in. Looking at rates of change. Falling prices. Hold on a second. All right, let's get back to it. Sorry. Let P be the function that gives the cost, P of T, in dollars of producing 1 watt of solar energy T years after 1977. Here's a table showing the values of P from 1977 to 1987, before y'all were born. Which expression best represents the average rate of change in solar cost between 77 and 87? Okay, so T is years after 77. So this would be 1977. And this would be 10 years later, 1987. So really, to calculate the average rate of change, we're going to calculate the function evaluated at 10 years minus the function evaluated at 0 years. Okay, let's back up a little bit. Average rate of change is, if you remember, slope y2 minus y1 over x2 minus x1. If we were to graph this value would be our x-axis because it is independent, it is time, and this would be our y-axis. This would be time, and this would be cost. Okay, we are decaying, but to calculate the average rate of change, we're going to do cost. It doesn't matter. Cost 2 minus cost 1. Oh, I don't know why I did X, sorry. Cost 2 minus cost 1 over time 2 minus time 1. That's what we're doing here. P of 10 is cost 2, so it's the price at 1987, minus P of 0 is the cost at 1977, over 10 minus 0. All right, so this is my change in y over my change in x. It's the slope of a line segment drawn between ordered pair 10 comma P of 10 and ordered pair 0 comma P of 0. So really I guess this would be y2, x2, y1, x1. I did P of 10 minus P of 0 over 10 minus 0. Okay? All right. It didn't actually ask us what it was. Which expression? Check. Okay, moving on. That was a lot of data for just a simple little answer. Here's a table and a graph that show the number of coffee shops worldwide that a company had in its first 10 years between 1987 and 1997. The growth in the number of stores was roughly exponential. Okay, here it's funny, they've labeled it 1987 to 97, and the number of stores is definitely growing. If you look, this is years since 1987, so this would be year 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, and year 10. So find the average rate of change for each period of time. Show your reasoning. So between 1987 and 1990, 87 and 90. 1, 2, 3. So we're going to do the number of stores. I think I can shrink this down. Oh, there we go. I think I might be able to write over here too. We'll see. So for part A, 1990 is year 3, but that's not what I want on the numerator. We need the number of stores at year 3. So 84 minus the number of stores at year 0, because that's 87, over year 3 minus year 0. All right, 84 minus 17, divide by 3. So we have 67 over 3, which is 22.3 repeating. B, 87 and 93. Let's do blue. 87 and 93. So we'll do the number of stores, 272 minus 17 over 4, 5, 6. 6 minus 0. 272 minus 17, divide by 6. That is 255 over 6, 42.5. So here, our average rate of change for those first 3 years is kind of small. Our average rate of change has gotten bigger. And that makes sense because if I connect 0, 1, 2, 3, I can't draw lines very well in this. But the slope of that line is sort of small, okay? And then the slope of the next line, I think I can do this. Ooh. From 0 to 93, which is year 6, the slope has gotten bigger, right? That's an increase of slope. Our average rate of change is increasing. Now let's do C. 87 and 97. So 1,412 minus 17 over 10 minus 0. 1412 minus 17, divide by 10. That's a much bigger slope. Our average rate of change has increased even more. Okay, now we go here. From 0 okay, the slope of that line segment is larger than the slope of the other 2 line segments. So our average rate of change has increased. It's the biggest average rate of change. All right, make some observations about the rates of change you calculated. Why? Let's see. No, we're not going to reset that zoom yet. So make some observations about the rates of change you calculated. What do these average rates tell us about the company, about how the company was growing during this time period, right? So we've talked about it. Our average rate of change has increased. Let's see. If we look, the average rate of change is almost doubled, okay? And the average rate of change here looks like it tripled. 42.5 times 3 is 127. Goodness, 139.5. Yeah. And this average rate of change from here to here is times 6. Okay, so our average rate of change is increasing more rapidly with each segment of years. So in the first 6 years, the average rate of change doubled. Almost doubled, right? Compared to the first 3 years. And then the average rate of change, so for the 10-year period, 10-year period, the average rate of change is, more than 6 times the first 3 years. Basically, what we're gleaning here is the average rate of change has not been consistent. This is not a linear function. The average rate of change would only be consistent if it were a linear function because the slope of the line would not change, but this is exponential. So exponential functions, the average rate of change increases if you're growing. All right, use the graph to support your answers to these questions. How well do the average rates of change describe the growth of the company in the first 3 years? So the average rate of change was 22.3. It's actually 22 1/3. It's pretty accurate. For those first 3 years, which was up to if we compared these two average rates of change, it's fine. Like 22.3 is pretty accurate. Pretty accurate prediction for the first 6 years. What I circled in that graph. Okay, it's a pretty accurate for the first 6 years, but after 92, it's icky. Not a good job. How about the first 6 years? Okay, that was 42.5. It's okay for the first 6 years. Okay, sort of the same as part A. But it's an overestimate for early years, for years earlier than this first 6, for early years, and a way underestimate. I can't do this. There we go. A way underestimate for later years. And then the entire 10 years, that was 139.5. Bad prediction of the actual trend. Okay, that slope is huge. So it's a bad prediction of the actual growth. I should use growth, not trend. Of the actual growth. Bad prediction of the actual growth. The slope is way too high for those early years, okay? All right, let f be the function so that f of t represents the number of stores t years since 1987. The value of f of 20 is 15,011. Find f of 20 minus f of 10 and say over 20 minus 10 and tell us what it says about the change in the number of stores. All right, so f of 20 is 15,011. F of 10 we have right here, 1,412. So the number of stores on year 10 is 1,412 over 20 minus 10. 15,011 minus 1,412 divide by 10. That is that slope is huge, that average rate of change. That's a pretty big number, okay? And what does it tell us about the change in the number of stores? So the number of stores, what did it do? Continued to grow. And a lot. So it continued to grow after 1987. 97, sorry. Oops. So the number of stores continued to grow after 1997. A lot. Okay, that means that what this represents right here is stores per year. I hadn't said that earlier. Very important. 1,359 stores per year. In 1997 to 10 years after that would be 2007, right? So those 10 years, the stores grew at a rate of 1,359 stores per year. If you look, let's see, the first 3 years were right here. If I look at the first 3 years, that was 22.3. That's 60 times faster than the first 3 years. And then 42.5. Oops. I multiplied and not divide. Okay, it's about 30 times faster than early on. So the growth was pretty small early on. I hate when that happens. But got really fast there at the end. Let me clear that. When the pen, like when the typing moves with me, I have to pause it and start it. 139.5. It's only 10 times faster. Okay, so we're still growing at an exponential rate, still growing quite a bit. So the stores continue to increase. So revisiting the cost of solar cells. See if I can make this bigger now. Oh, because I wrote on it. Hold on, page width. Oh, that'll work. So here is a graph you saw in an earlier lesson. It represents the exponential function P, which models the cost in dollars of producing 1 watt of solar energy from 77 to 88, where T is years since 77. So 77 is year 0. Claire said in the first 5 years between 77 and 82, the cost fell by about $12 per year. So 77 and 82, first 5 years, I'm going to see if I can put a line in there. So insert a line. I know this is taking me a long time. So here to there. So that's what that is representing. In the first 5 years, the cost fell by about $12 per year for the first 5 years. So this right here represents the slope of that straight line, of that linear function. Okay, so that is my slope. The cost fell by, but in the second 5 years, between 83, let's see if I can copy that. Cool. And then 83 and 88, so from here to there, that slope is smaller, so our value should be smaller. $2 per year, right there. Okay, so that's the slope there. Show that Claire is correct. So I can actually do the math. So we'll stick with blue. I do change in y, so 80 minus, I don't know, what would that be? About 19 over 0 minus 5. 80 minus 19, divide by -5, 12.2. So it's negative 12.2. That just shows a negative average rate of change, a negative slope. So dollars per year. Let's go to green for this one. I'm going to go, I used 19 for that one. So 19 minus, let's see, 10, 20, 5, I don't know, 3 over 5 minus 11. 19 minus 3, I get 2.6. So my calculations are a little off, but that's okay. Claire is correct. If the trend continues, will the average decrease in price be more or less than $2 per year? It's going to be smaller, so less than $2 per year, because we're decaying, so our slope is going to continue to get smaller and smaller. And then if you would like to try the "Are you ready?" send me an email with lesson 10. Okay? Just so I know what I'm looking at, but I'd love to hear what you think about that. And there is our summary. All right, good work today.